red patches here are the crustal magnetic fields, and so they form small umbrellas around localized regions of the surface, and divert the solar wind around these localized regions. But all these regions up here, the solar wind just plows right into the atmosphere, and it energizes, ionizes, and energizes the atmosphere, and it gets stripped off. And you see these trajectories, these orange trajectories. These are ions getting accelerated away from the planet and lost down into the tail region. And so, and here are more ions leaving the tail of the planet. So this atmospheric stripping process is much more effective at Mars. And so the idea is the basic scenario that we're trying to work from is that Mars started off like the Earth did, because we know that the magnetic fossils that we see on Mars today tell us that Mars was once looked like this, a dipole field like the Earth did. And so that's going to protect the planet from the solar wind, and so the loss rate of the atmosphere is going to be much less back then. And we know at this time Mars had a warm, wet atmosphere, Earth-like pressure, maybe a third of a bar to a bar, and possibly even a global ocean or a large-scale ocean. And so, at some point soon after, within a couple 100 million years of the end of the late heavy bombardment, this went away. This magnetic field went away, and then suddenly the planet was exposed to the solar wind, and it can strip away ions, both in the process shown here, and also in bulk. This is sort of a bulk loss process. And if you've ever seen images of comets, astronomers taking pictures of comets, sometimes you'll see a piece of the tail getting stripped off, and it'll look like it's flowing back from the comet. And that's actually a process whereby the magnetic field rotates, and it actually pinches off a piece of the tail, and there's this piece of tail plasma that gets pulled down with the solar wind because it got pinched off from the comet. And a very similar process happens along the terminator region of Mars. So there are instabilities in the upper atmosphere, and then if you have magnetic twists coming through there, they can pinch off pieces of the atmosphere, and drag them downstream. And so this sort of bulk escape process also works on planets as well as comets. And then we get down to the desert that is Mars today. Space Flight Center. There's three what we call electrostatic analyzers for measuring ions and electrons. Two of these measure ions. This one focuses on planetary ions. These are the cold ions that are in the ionosphere of the planet, so mostly oxygen, carbon dioxide, those kinds of ions in the lower atmosphere of the planet. And this is the one that's going to actually measure the ions getting accelerated at low altitudes up to escape velocity at high altitudes. And so this has a very wide energy range that can measure all the way down to thermal velocities of much less than a kilometer per second, all the way to hundreds of kilometers per second. So this is the one that's going to actually watch the ions getting stripped away and carried downstream. This one measures the solar wind, so this measures the input flux of hydrogen and helium into the planet. And this is the instrument that I'm the lead of. This measures medium energy electrons, so thousands of degrees up to tens of thousands of degrees. And this one is going to be used for measuring what we call the magnetic topology. And so that's a kind of a fancy word. And what it means is that if you do an iron filings of a bar magnet, you can see the magnetic field lines. And so the magnetometer is going to be measuring the strength and direction of the magnetic field lines. And this instrument measures where they go to. So this one can tell you whether they go into the ionosphere, whether they go out into the solar wind, and how everything connects up, how the field lines all connect up. And so that's what this instrument does. There's a solar energetic particle detector. This is measuring those big solar energetic particle events, the coronal mass ejections. This measures the particles that come from those events so that we can correlate the presence of these events to the response that the atmosphere has. These are the magnetometers that work hand in hand with the electron instrument here. This is the extreme ultraviolet sensor, and what this does is it just looks at the sun, just stares at the sun, and measures the solar spectrum. So one of the key things for this mission is to understand the atmospheric chemistry in the upper atmosphere. There are chemical reactions that, well, first of all, the carbon dioxide is going to become dissociated, and there are chemical reactions that are exothermic that can result in hot neutrals. So some of the hot neutrals are oxygen, so there's an oxygen corona around Mars that's basically formed from exothermic reactions from the recombination of oxygen following its dissociation from CO2. And so, and there are other exothermic reactions that result in these coronas of stuff, of material, and these things extend way out into the solar wind. And so once you have this corona that extends way out there, it's sitting out there on the sunlight. Eventually it's going to get ionized, and the moment it's ionized, it suddenly sees the solar wind go by it, it'll get picked up by the solar wind and dragged down stream of the planet. So this is one of the important loss mechanisms from Mars. And so let's see, that's this guy. And then Langmuir probe and waves, and what these do is they study very cold electrons. And so both of these measure electrons. This measures the medium energy and high energy electrons, and this one measures the very cold electrons. And so it measures the structure of the ionosphere, where the ionosphere density falls off at high altitudes. And it can also measure the, remember I talked about these comet tail pieces of ionosphere that get stripped off. This can measure the extent of those atmospheric parcels that get stripped off. And it also measures waves, and so you have this plasma surrounding the planet. And there's a host of different wave properties, different kinds of waves that can propagate through this plasma. And some of these waves are important for actually energizing the particles. The waves can interact with the oxygen ions in the ionosphere and give them energy. The ions are gyrating around the magnetic field lines, and so they gyrate with a certain frequency. So if you pump them with a frequency that's equal to the frequency in which they go around the magnetic field lines, you can give them energy. They can go faster and faster and faster, and eventually they have escape velocity. So this instrument is measuring those waves to see if that process is important.